Hello, and welcome to Chapter 3, Chemistry of Organic Molecules. If you'll recall, in our last lecture in Chapter 2, we learned that all living things were composed of the same elements. In this chapter, we're going to learn how those atoms of those elements come together to form molecules that make up all living organisms. We learned that living things are made of hydrogen, oxygen, carbon, nitrogen, sulfur, and phosphorus. And we're going to learn that these organic molecules, which are comprised of these building blocks, make up all living things, or things that we call organic. When we use the word organic, it implies that something has been living or is living currently. Inorganic then would be the non-living. So all living things are made of the same molecules. These molecules are carbohydrates, lipids, proteins, and nucleic acids. So hydrogen, carbon, oxygen, nitrogen, sulfur, and phosphorus come together in the form of these molecules. First of all, before we get started, let's just compare organic and inorganic molecules so that you will get an idea of how they actually differ from each other. Organic molecules contain covalent bonds. These are the bonds that we talked about in Chapter 2, where atoms actually share electrons. Inorganic molecules contain primarily ionic bonds, and we learned in Chapter 2 that this is when atoms donate electrons to another atom, creating an atom with a charge, and we call those ions. Inorganic molecules contain ions. Organic molecules always contain carbon and hydrogen. As a matter of fact, organic chemistry has sometimes been called the chemistry of carbon. If I were to give you a list of molecules and you were to be asked to pick out the organic ones, you would definitely look for those molecules that had carbon in them. Inorganic molecules are very small compared to organic molecules, which are very, very large. As a matter of fact, in a few moments, we're going to refer to organic molecules as macromolecules. They're so large. And inorganic molecules are found in non-living things, and organic molecules are found in the living. Since we said that organic molecules contain carbon, let's talk about carbon for just a moment. Carbon's atomic number is 6. This means that carbon atoms have 6 protons. With 6 protons, if the atom is electrically neutral, which we talked about in Chapter 2, that means it also has 6 electrons. With 6 electrons, they would configure themselves with 2 electrons in the first shell and 4 electrons in the second shell, or the valence shell for carbon. So carbon has 4 electrons in its outer shell. Carbon atoms like to form those covalent bonds, which are very, very strong bonds. So we can actually have carbon atoms that are bonded to other atoms or different atoms. Carbon can be bonded to other carbon atoms either. So what we find in these organic molecules are carbon atoms bonded to other carbon atoms, bonded to other carbon atoms, and with sharing hydrogens also, forming something called a hydrocarbon chain, which looks something like this. So let me make sure you understand what you're looking at here. This carbon atom is bonded to this carbon atom, sharing a single electron. These single lines here indicate that there is a single electron shared between the 2 carbon atoms. This carbon atom is sharing a single electron with that hydrogen. It's also sharing a single electron with that hydrogen and that hydrogen. So this carbon atom thinks it has a full outer shell or a full valence shell. As you see this molecule, this hydrocarbon chain, there are no charges associated with this construction. So this molecule, as we see it right here, this hydrocarbon chain, is actually hydrophobic, or it's repelled by water. Hydrocarbon chains vary in length. You could actually just have 1 carbon and 1 hydrogen, and that would also be called a hydrocarbon chain. In these organic molecules that we're going to talk about, we'll see these hydrocarbon chain structures with other atoms attached to them. We call these clusters of atoms that tend to hang out together. We call those clusters functional groups. Functional groups attach to these carbon chains. And keep in mind, it's a group of atoms that has a certain pattern. And we see that pattern occurring often because of the bonding of these atoms together. And these groups of atoms actually have properties associated with them, so that when we see them attached to these hydrocarbon chains, we know that those properties came with the cluster of atoms. So these functional groups always behave in a certain way. And when you see a functional group attached to a hydrocarbon chain, it can actually change the polarity of that area of the molecule. So here we have a hydrocarbon chain right here with a functional group attached. This is a hydroxyl. It brings with it a negative charge, and so it would change the polarity of that area of the molecule. So let's make sure you understand. Molecules with only carbon and hydrogen are hydrophobic. They're nonpolar. They're not attracted to water. Molecules, you can take those hydrocarbon chains and add a functional group to it, and it will change the polarity of the molecule, making it hydrophobic or attracted to water. Okay, in a few moments we're going to actually see some molecules that are isomers. An isomer is an organic molecule that these molecules have the identical molecular formulas. Remember the molecular formula, it's right here. The molecular formula tells us the elements that are in the molecule and the numbers of atoms of each of those elements it takes to make that molecule. So this is glucose, and if you'll notice, glucose is C6H12O6. Well, this molecule is fructose. Its molecular formula is also C6H12O6. So both of these molecules have the exact same identical molecular formula. However, they are two very distinct substances. They are not the same, because if you'll notice, the arrangement of atoms is quite different. Take a look at this carbon and its bonding pattern, and then look at this carbon, and you can see that the molecules are not the same. They are found in two different places. They are two distinct substances. Okay, so we call these organic molecules macromolecules because they are so large. They are large, very large molecules composed of smaller molecules. So we take these smaller molecules and bond them together to form the large molecule. We're going to call the smaller subunits of each of these monomers, and when they bond together, we actually call the large molecule a polymer. Mono means one, poly means many. You can almost think of these molecules as a freight train. You know that the freight train is large, but it's made of individual train cars that are bonded together to form the entity of the freight train. So you could think of the individual units as the cars, and the large train, that would be the polymer. So we have monomers, individual units that bond together to form a polymer right there. So definition. Polymer is a long molecule consisting of many building blocks called monomers. And keep in mind, as we talk about these groups of organic molecules, the carbohydrates are going to have their individual monomer. Proteins are going to have a different monomer, and nucleic acids are going to have their monomer. So each class of macromolecule has a specific monomer. And we're going to talk for the next few slides about how to put these together, how to put the monomers together and take them apart. But for instance, proteins, which we're going to talk about later on, the monomer of a protein is an amino acid. You may have heard of those before. So let's talk about how to build these macromolecules and how to break them down, because the same reaction is used regardless of the class of molecules. The same reaction builds carbohydrates as builds amino acids. So let's talk about how to put one together, how to put these molecules together. When we build a polymer, and it doesn't matter, again, if it's a polymer of amino acids or if we're making a carbohydrate or if we're making a nucleic acid. If we're building a polymer, the reaction is called dehydration or condensation synthesis. So let's think about those words for just a moment. What does the word synthesis mean? You learned in your root words that syn, S-Y-N, means to put together. So the word itself tells you what's going on here. Synthesis means we're putting something together. The word dehydration, or some books actually use the word condensation. Both of those words imply that water is being taken out. And that's exactly what's happening in this reaction. Dehydration synthesis is when monomers actually join together and water exits the reaction. Take a look at the illustration for just a moment. This is a generic illustration. It could be a carbohydrate we're building. It could be a protein we're building. This would be the monomer right here. We actually have a hydroxyl on one end. We have a hydrogen on the other end. This, again, right here, this is a polymer. You can see that we've already joined 3 monomers together. So we're going to join this monomer to this polymer. So how do we do that? Well, dehydration synthesis. We're going to remove the OH from the monomer here, and we're going to remove the H from the polymer here. Those two are going to form a water molecule, and where those once existed, now we have a bond right here. So we're joining monomers with dehydration synthesis. We're going to remove a water molecule, and we're going to form a bond there. That's the synthesis part. So this is how we would build a protein. This is how we would build a carbohydrate, etc. So now let's think about what we would have to do to break this polymer down. This is my polymer right here. So how am I going to break this bond now? When we break bonds, when we break down polymers, it's called hydrolysis. Hydrolysis, think about the word. What does the suffix lysis mean? This was one of your root words. Lysis means to break down or to burst. Hydro implies water. The word is telling you what's happening. We're going to break the bond using water, hydrolysis or hydrolysis, if you would like to think of it that way. This is when we're taking a polymer. Here's our polymer right here, and we're going to break it into monomers. So we add water. Here water is going to split. Here's the H, here's the OH, and now we have a monomer that has been broken apart from that polymer. So it's the reverse of dehydration synthesis. We're going to add water to break the bond. Okay, so let's summarize this. How do we build an organic molecule? How do we build and break down? We have monomers. We build a polymer with dehydration synthesis where water comes out. How do we break down a polymer? We do that with hydrolysis. We have to have water coming in to break the polymer into individual monomers.